All right. Hello, everybody. My name is Michael Taschuk, and I'll be talking to you today about solar simulation and LEDs and how we use them to advance future technologies. I'm going to take a moment to pause and consider all the things and objects and technologies that interact with sunlight over the course of their daily lives or years of use. So this goes for everything for like the most advanced satellites that go up into orbit, the clothes and wearables that we use, cosmetics or sunscreen that we put on our bodies, and up to textiles and the paint that go into our automobiles. In addition, there's a wide range of photovoltaic applications that require to function by interacting with sunlight. The thing that draws all of these together is the need to test them in advance so that you can verify the performance before they go out into the field. If you don't get this right, your photovoltaic cell might not work, the paint on your car might age, or your satellite may not function once it's in orbit. And this is really at the heart of what we do here at G2V Optics, is we see our mission as accelerating solar, aerospace, and materials innovation with engineered sunlight, which is the output of the solar simulators that we make. In my talk today, I'm going to discuss our background and history, introduce solar simulation in terms of the kind of problem that we're trying to solve, cover the introduction of LEDs to that technology, and then show what's truly possible with a high-quality LED solar simulator. I'll end up covering some applications from our customers and then discuss the future of solar simulation as we see it here today. So I'm going to talk first about us. This is G2V. We're a team of 30 people headquartered in Edmonton, Canada, and we've been in existence for about 8 years. So a highly dedicated, highly skilled team has probably designed more solar simulators than any other group in the world. We have customers in over 40 countries, including many Fortune 500 companies and top research institutions around the world. An example or list of names for some of the companies that we've had the privilege of working with are given here. And one of the things that's the most exciting about our jobs is the opportunity to see behind the curtain a little bit with these companies and understand what's coming next. And we get to play a small part in helping these amazing organizations deliver their next innovation to the public. And this is true not only of companies or institutions like NASA, but also MIT and companies like Tesla or Amazon. And it's been an amazing privilege to be able to get a narrow view into what's coming next. The next section, I'll talk about the solar simulation problem. And this is what all these companies come to us for, is our ability to duplicate sunlight in a tested way. So we'll start with the actual object that we're trying to duplicate. Our sun is a G2V star, and this is where our company gets its name. It's a 5,800 Kelvin blackbody source and 150 million kilometers from the Earth. Solar simulators aim to duplicate the sun's spectrum and intensity. And so as one moves from where the sun is to where Earth is, you preserve the black body characteristic, and that's this curve shown here. So this is the normal kind of black body curve that you would see. And you get a total irradiance of about 136 milliwatts per centimeter squared. And so this is the environment that a satellite has to contend with lots of UV and a long tail of infrared. As one moves through the atmosphere to ground level, you get a number of absorption features. So one gets water and other gases taking notches out of the filter, and the shape changes a little bit. The absorption of the atmosphere also drives the intensity down to about 100 milliwatts per centimeter squared. And so the changes that I've shown you here really come from the interaction of the sun spectrum with the Earth's atmosphere. And that can be quite a complicated thing. The slide here shows the sun. So if we take this initial position, so imagine the sun directly overhead when you're standing on the Earth. And so that is the sun up at the zenith. And as it transmits lights to the top of the atmosphere, we call that air mass 0. As one goes through the atmosphere down to where you're standing, we have air mass 1 shown here. Oh, excuse me. Air mass 1 as shown here. But the sun doesn't stay overhead all the time. What ends up happening during the day is that it shifts around, and so you end up going through more and more atmosphere as you end up or go towards sunlight as you go towards sunrise or sunset, where the blue scatters out, which gives us the color of the sky, and you're left with the red, the nice colors that you see in the morning. So the broad range of spectrums here requires some standardization. And so the AM1.5 spectrum shown here, this first one, has been selected by the community, the photovoltaic community, as a representative spectrum for testing. This really highlights the need and role that standards play in this kind of field. And so ASTM G159 defines the solar spectrum for AM1.5, and it's the default that is used in testing most material systems. IEC 60904 and ASTM 927 define solar simulators and tell you how to classify them. So many of you will be familiar with Class AAA as a designation for solar simulators, and this is a grading system for the three primary characteristics of a solar simulator, and that would be temporal instability, spatial uniformity, and spectral match. And so if you're at the top end of performance, you can get an A+, and there's also grades of B and C depending on the performance. In this next section, I'm going to go through each of these and spectral deviation and spectral coverage and discuss how they contribute to a solar simulator's performance and the kind of data that you would use to assess them. So we'll start with temporal instability. And so temporal instability measures peak-to-peak variation in the irradiance. This plot shows time across the horizontal axis and the number of suns on the vertical, and each dot is a measurement from a solar cell under a simulator. So what you're looking for here is a stable illumination over a long period of time. So you measure the top one and the lower one for your experiment, and that range gives you the temporal instability. The reason this is important for experiments is that it helps with not only long-term aging experiments, but also day-to-day runs where you're doing tests every day, and you really want to be testing under the same conditions for different experiments. The next one is spatial uniformity. And again, here one measures from the peak to peak variation of the illumination plane. This plot shows a 1 meter by 1 meter area. So the illumination here is where you would put your test device. And so spatial uniformity speaks to the homogeneity of the light across the illumination plane. And so if you're testing an array of solar cells, you want to be sure that the test in this area here is the same as this area. Or if you're moving things around, you want to be sure that the solar irradiance that you're trying to simulate actually has the right characteristics. So then we move on to spectral match, which gets a little more complicated. And so across the bottom, I have wavelength. And so this is 400 nanometers out to 1100 nanometers. This wavelength range corresponds to blue, and 700 corresponds to red. And so human vision is really constrained to this range here. All of this is in infrared, and we feel that as heat. Because of the time in which the standards were generated, it wasn't actually possible to do fine-tuned adjustments across the spectral range. And so they decided to break it up into bins. And so this line here represents the first bin from 400 nanometers to 500 nanometers. The vertical axis corresponds to the percent of the total irradiance of your source. And so to be a Class A spectral match, you have to be between this red line and between this blue line here. And so this dot represents an empirical measurement for the simulator here. And because it's within those two bounds, it's a Class A. So similarly, as you go across the spectrum, we have a number of 100 nanometer bins, and these dots show that for every part of this spectrum, this simulator is in compliance. And then one runs from the 900 to 1100 nanometer bin and a single dot there. One of the differences between ASTM and IEC is that the bins are starting to change and be extended out to 1200 nanometers. One of the challenges here is that with LEDs, it's possible to adjust the spectrum on a much finer scale than what is shown here. And so the IEC committee has added a couple of optional characteristics that people should be reporting, and one of those is spectral deviation shown here. And so if you take this black line as representative of the AM1.5 spectrum and this red line here of the spectrum that is being illuminated, and you wanted to evaluate spectral deviation, what you would do is evaluate all the areas in which you're not close to the black line. So this red line down here has a large gap between it and the target spectrum up there. Similarly, this peak rises well above the AM 1.5 line, and so you end up adding that area as well, and so on across the entire spectrum here. And so every one of these red areas corresponds to the individual components of spectral deviation, and you integrate that to get to the overall value. And so spectral deviation for a high quality solar simulator is low. And the reason this is important is that your experimental results and projecting the results of your lab experiments out into the field, the fidelity of that is much improved if your spectral deviation is low. The other optional figure of merit that's in the IEC standard now is spectral coverage. And so we'll talk more about this later, but LEDs emit in a very narrow wavelength compared to conventional sources. And so this spectrum has got coverage from this edge of this green line here to this green line over here. And so the idea is that you report the region in which your simulator has more than 10% of the light for AM 1.5 so that people can evaluate it. Here, this would correspond to a spectral coverage of about 2/3. So all of that combined gives you a sense of how you should be characterizing solar simulators and the kind of tests or figures of merit that you need in order to evaluate the performance of an instrument. And so in this next section, we're going to start to talk about the development of LEDs and how they have contributed to solar simulation as a technology. In this figure here, I show 3 different sources. So I've got xenon at the top, metal halide in the middle, and LED down at the bottom. And each source has different advantages and disadvantages. And so xenon and metal halide are nice plasma sources, and so they've got a good black body curve. You can see kind of the characteristic shape of that there. But there's atomic emission features that are superimposed on top, and that's true of the metal halide as well. For LED, you can have a really smooth curve that mimics the black body curve really well across a certain range. And this is the spectral coverage that I just showed you earlier. So one can achieve a really high quality match where there are LEDs to illuminate, but not out here. And so the challenge then becomes is for a given experiment, one has to evaluate the different sources and make sure that for the physics or the material property or the performance that you're trying to test, that your light source is actually probing the right behavior. And so if one needs to understand the interaction of the far infrared with your material, a xenon or metal halide source would be better. If one needs to study photocatalysis, having a smooth source that duplicates the UV emission of the spectrum will be a better choice. And so it really depends on what you're trying to achieve. Similarly, there's trade-offs when it comes to the stability and time. And so those of you who still have incandescent bulbs in your home will know that they fade and age over time. And the same is true of xenon and metal halide bulbs. And so one gets a drift as the experiment changes over time. One of the strengths of LEDs is they're incredibly stable across many thousands of hours of use. And so for long-term experiments where one is aging for thousands of hours, LEDs can be a very solid source if you can accommodate the spectral restrictions. And those really come from the way that LEDs were invented. And so this figure shows, or developed, I should say, this figure shows some spectral characteristics from LumaLEDs, and they're optimized for the human vision range. This is the 400, and so that's the blue again, and the red over here at 700 nanometers. And so most of LED technology has been driven by human vision needs, and so most of the attention has been focused on the 400 to 700 nanometer range. Over the past several decades, there's been a lot of research done on extending the LED capacity into the ultraviolet and into the infrared. And that allows the LEDs to cover the entire spectrum of the sun, but one has to be careful to select the right LEDs. The other half of this comes in terms of the emission efficiency for the LEDs. And so this shows years across the bottom, and this is lumens per package or lumens per LED. So the numbers don't matter. This is a logarithmic scale. The point of this is that there's a exponential growth in the number of lumens per LED that can be produced. And so it became really clear at about 2010 that LEDs were in the range where you could actually duplicate the intensity of sunlight. And that's when you started to see LED solar simulators appear, first in the scientific literature and then commercially a few years afterwards. One of the challenges with LED solar simulators is that you have to manage a number of different sources. And so conventional technologies with xenon or other bulb sources have one source, and that's relatively easy to manage from an optical perspective. You can apply well understood lenses or filters in order to correct the performance. But for an LED solar simulator, you often are dealing with hundreds or thousands of LEDs. This image shows a 2x4 meter system that we built for one of our customers, and we had to individually characterize all of these in order to actually provide the right performance. The reason this matters is if you look here, you can see one LED at 100%, another at 98%, and one at 103. So if you think about the contribution from each of these LEDs on the illumination plane, you get 3 peaks, but the superposition of them is a little bit irregular. And so if you're going to be building an LED solar simulator or a multi-source device, you have to be able to detect these variations and then compensate for it in order to provide the right level of detail. In addition to that, you also have to manage the colors. And so the plot I showed you just before was assuming monochromatic sources, but in fact, you have to use a bunch of different LEDs to build up the spectrum. This simplified example here shows blue and red and the overlap between those colors. And then further out, one can achieve really high uniformity, but you do have to deal with the components separately. So it's necessary to optimize the red as well as the blue LEDs shown here in order to provide a spectrum that provides what we call chromatic uniformity. So with all of that combined, I think there's one last thing that I want to talk about before we move on to showing what is possible with LEDs, is there's a bit of a loophole in the standard, and this plot shows or illustrates what it is that I mean. So this is, again, wavelength across the horizontal axis and spectral intensity this way. And we've chosen 7 LEDs here, 8 LEDs, that corresponds to a wide range of illumination wavelengths. And so we go from 365 all the way up to 1100. Technically, this is a Class A solar spectrum. And so I told you earlier that the bins over which one evaluates a solar simulator are these 100 nanometer increments, but you only have to hit an average power between 400 and 500 nanometers. And so if you put this peak well above the target background here, this line is the AM1.5 spectrum again, you can actually achieve the average power in that bin, but you're not really mimicking the solar spectrum in a meaningful way. And this is really where the spectral deviation and spectral coverage figures of merit come into play. So now the question, having left with this, is what is possible with a well-tuned, well-characterized, and well-done LED solar simulator? And so in the next section, we're going to discuss exactly that. This figure, again, shows wavelength and intensity on the vertical axis, and the blue line is the AM1.5G spectrum, and the white line that is just traced out is what is possible with one of our instruments. You can see with careful selection of the LEDs, you can minimize the spectral deviation around the AM1.5 spectrum, and it's possible to get coverage of the overall AM1.5 band, including and extending well past 1600 if you are so inclined. Similarly, with spatial uniformity and careful control of all the LEDs that make up a solar simulator, it's possible to achieve uniformity well under 2%. And one of the most interesting things about this is that if you manage it well, you can actually tile these areas together and build up coverage over a much wider area. And third, we have temporal stability. This plot shows elapsed time in hours and the measured power within the Class A bands. As you can see this come on across the plot, you can see it's easy to stay well within a Class A range over many thousands of hours and provide very solid temporal stability over your experimental lifetime. So this at a technology level is what is possible. When it's wrapped up into products, this shows how we instantiate these systems. And so this is our small area solar simulator called the Pico. And it covers an illumination area of 2.5 by 2.5 centimeters, has up to 32 channels. And one of the key advantages of this really is driven from the fundamental LED technology, that there's no bulbs, no physical filters, no field calibrations. All of this is done by us in the lab here. Similarly, the same technology can be deployed across a much wider area. This is what we call the Sunbrick. It illuminates 25 centimeters by 25 centimeters and up to 36 channels. The key thing about this is the modular design. And so you can't see it here, but these are able to hook together and tile across arbitrarily large areas. The biggest we've ever built is 8 square meters, and you can go much larger than that if your experimental needs require that. But the hardware itself is not enough, right? With the kind of LED management technology that we have, it's possible to control it by software. What this opens up is a brand new capability for solar simulators. So if one has a very complicated experiment or needs really precise control, especially if you're changing it in time, an LED solar simulator provides unmatched capabilities. So for our instruments, we have a graphical user interface for simple applications. We have an interface that we call One-Click Sun, which allows you to simulate sunlight for any location. That plot I showed you earlier of the varying sun angles, it calculates all of that so you can choose location and time of day, and it'll produce the spectrum for your instrument. For cases where one has to integrate with other lab equipment or do really powerful experimentation, the Python API or the LabVIEW module are available, and we have code examples and support that are available if you need help getting started. In addition, we have a number of partners worldwide, not only amongst our customers, which perform an amazing network of expertise, but there's lifetime application support and a global VAR network that you can rely on for support. Okay, so we're going to take a moment here, and we've shown you the LED technology, how it gets instantiated into products, and now we're going to focus on what people are doing with them. And so I showed you earlier this plot, which has a bunch of different material systems and applications that people might use LED solar simulators for. And in the coming slides, I'm going to show you how some of our customers are using our technology for their applications. We'll start with NASA. And so NASA approached us a couple of years ago with the requirement to test their OSAM satellite before launch. So that satellite is shown here, and they are looking to service satellites in orbit to extend their lifetime. And so this will be things like refueling or repairing, and there's a set of robotic arms and machine vision here that helps the satellite and operators perform the repairs in orbit. But in order to test that, they have to be able to duplicate sunlight as it exists at AM0 and across a very wide range. And so we built them a very large array. This is 1/4 of it shown here on the right that duplicated the AM0 spectrum as experienced by the satellite's cameras. This is going to allow them to test the satellite before it launches, which is critical for ensuring mission success, and also continue to duplicate the performance of the satellite with a digital twin on the ground. Continuing in the aerospace vein, we have a collaboration project with CNES, which is France's national space agency. They're planning a mission to the Martian moons. And so in order to make sure that the spacecraft arrives at the right place at the right time, it's really important that it knows where it is and which way it's pointed so that when it makes a maneuver to change its orbit, it's going in the right direction. And so CNES is using a Sunbrick, you can see it back here in the corner, to test their attitude and orbital control system. And that's a device that determines orientation based on incident sunlight. The next application here is for Perovskite silicon tandem solar cells at Arizona State University. Silicon PV has been scaling up really dramatically over the past several years. And as the research community is looking forward to see what should be deployed in future generations of the technology, one of the most promising candidates that they've landed on is something called a Perovskite. And the vision here is that the Perovskite can be integrated on top of a silicon cell. But this complicates the characterization, as it's necessary to be able to get the spectrum balance correct between both of these. And this is a place where ASU is able to use our technology in order to correctly illuminate not only the combined device, but address the individual devices that make up their planned tandem cells correctly and develop their technology. Similarly, we have Raleigh Solar Tech, a company in the east of Canada, which is scaling up perovskite cells from research to commercial manufacturing. And so that's a very challenging technological development process where they have to scale up from the small devices you see here to something that is commercially viable. They're using our Sunbricks to help with that. This next application is very interesting and applied for advanced solar cell materials. And so Sinton Instrument is a world leader in photovoltaic materials characterizations. And together with them, we provided a customer the combination of their diagnostic capability with a very high quality LED light source that allows better spectral fidelity for the measurements that Sinton and customers were making. This application is for a company called Switch Materials. And so in modern cars, there's often a roof that is glass or the ability to tint a window in real time in response to changing outdoor conditions. And this company had developed an electrochromic coating that could be used on these glasses. The challenge that they had was to ensure that the system would work anywhere in the world because their automotives might be deployed anywhere in the world. And so they came to us with the need for a very large area system that could duplicate sunlight, not only in Canada, where they were located, but say Mexico, Africa, Asia, right? All of these environments have different sunlight conditions, and it's necessary to prove their technology in all of them so that they can scale up. There's been a recent trend towards wearables and other technologies that we wear. So our watches and our clothing are getting more sophisticated. And we have a number of customers that are interested in improving or doing QC on their materials or products under the sunlight that they will be deployed in. That includes things like smartwatches or textiles that go into advanced clothing. One of the final applications I have to show you today is solar fuels. And so this is a parallel technological track with silicon PV, but designed, instead of converting photons to electricity, they convert photons to fuel. And so through a photocatalysis process, they're able to do water splitting and generate hydrogen. And so this customer is working with one of our arrays in order to test their scale-up prototypes so that they could characterize performance before they were deployed at scale. And finally, one of the ones that we're most excited about is our collaboration with NREL. NREL is one of the world's leading research institutes for solar and has a world-renowned characterization lab. And they have selected G2V and our technology to understand how LED solar simulators perform against their existing technologies and learn with us how to adopt it into future projects and characterization efforts. Okay, so in the next section here, we're going to talk about solar simulators of the future and how we see the development of the technology going forward. For industry, there's this enormous pressure to scale up manufacturing volume and speed. Is the goals for deployment of silicon PV is up at the multi-terawatt scale on a per annual basis. This is what they're scaling to build. So in order to support that, the rapid changes in cell size and module size really demands improved modularity for production environments. And so the Sunbrick and subsequent products will address this need and support their ability to adapt to the changing demands of the marketplace. In addition, there's an integration of continuous and flash capabilities. And so a lot of industrial production is done with flashes, but it's also possible to get very interesting and important information from continuous illumination as well. And future LED solar simulators will be capable of doing both of these. The second major thrust that we see in terms of advanced LED solar simulators is to support the next generation of solar technologies. So we just talked about the industrial side and their needs, but it's also important to recognize the material set is changing as well. And so materials such as perovskites, perovskite silicon tandems, all have different testing requirements. And so a next generation solar simulator will have improved chromatic uniformity, extended bandwidth to accommodate the broader range that these materials absorb, and improved support for tandem and multi-junction modules that will be coming down the line in future years. The third part of this is self-calibration. And so it's crucially important for both industry and research that you be able to trust the results that you're getting. A conventional solar simulator can often age, the bulbs change over time, and it's important to be able to assess that in real time so that you don't ship a bunch of product that isn't fully tested, or you don't trust a research result that you shouldn't. And so with LED's technology, there's this opportunity for this really tight feedback loop within the instrument that allows you to monitor the simulator performance in real time and adjust so that your test results remain in compliance. And finally, I want to ask the community here and the audience, if you've got a demanding solar application that you would like to talk to us about, we'd be very interested to hear from you. Our objective is to accelerate your development, and we are well positioned to do so with the set of technologies that we have. In the final part of our talk, we'll go into a Q&A, and I'll leave my contact information here up as we speak, so that if you don't get your question answered or there's not enough time, please reach out to us afterwards, and we'd be happy to have a conversation.